So shall we begin now?
Yes, I think I can begin. Let me share my screen. I will start.
Yeah, just to give a very brief introduction of you and the topic for today.
Okay.
Yeah, hello everyone. Hello, Professor. Today we invited Professor Jean-Claude Franchitti from New York University to share cloud PaaS and machine learning applications with us. Dr. Jean-Claude's teaching and research interests include database systems and software engineering with an emphasis on large-scale software architectures and business solutions. He has published articles in numerous refereed publications, including the Proceedings of Third International Conference on Cooperative Information Systems, Proceedings of the Sixth International Workshop on the Persistence of Object Systems, and the 16th International Conference on Software Engineering. So now, please allow me to give the stage to Professor Jean-Claude.
Hello, everyone. So I hope you can hear me well. Let me know otherwise. So it's a great honor for me to be able to discuss this topic with you today, and welcome everyone. So and thank you for the introduction. So as stated, the topic of today is going to be on looking at technologies that are enabled by cloud computing, and in particular what we refer to as platform as a service, as well as what can you do with machine learning on the cloud, right? So that's what I would like to focus on. So it's kind of a very, I would say, convoluted topic. There are many different things that are related to this. So let me try to bring up the slide set so that you can see it better. So obviously, I'm going to try to reduce the size of the discussion, right, or the presentation to about 40 to 45 minutes, so there is time for questions. I may not be able to do that, so it may drag to like 55 minutes or so, but I will do my best. So I may skip some of the topics, but I will try to give you a sense of what's going on, right? So what I would like to do is first give an introduction of myself and what I do, and what led me to this topic today. I want to spend a little bit of time explaining what the platform as a service is about, and then focus on machine learning and real life applications of it, as well as maybe an epilogue as to where we are with technology today and what's going to happen next, right? So this is a brief summary of who I am. So that's kind of my program. 40 years of experience in a mixed, kind of what I would say like academic and industrial type of involvement. So I worked for about 40 years in the industry, and I've spent about that much time as well in the academia. I'm currently at New York University as a professor of computer science at Cohen Institute, and I'm also the founder and CEO of a company called Alchemy Inc., which is an AI-centric company. I got my PhD in computer science from University of Colorado at Boulder back in the early 90s. And as I said, I've been involved in the senior leadership of many, medium to large companies in various industries, about 7 or 8 different industries, including like banking, financial services, insurance, pharmaceutical, healthcare, whatever. And so if I have time, I will explain briefly why I was interested in looking at so many industries, but I learned a lot, and it enabled me to actually build solutions for these industries. That's really in a nutshell the reason why I'm interested in this. So I have actually been involved in research projects for research agencies in America like ARPA and National Science Foundation. I am a member of various standards committees, the OMG Cloud Working Group today, where I published some practical guides to actually try to standardize cloud technologies. And I've actually built actual solutions in the industry, one of them known as Data Stage, which was a solution that I built in the early 2000s that is now being maintained still by IBM. So this is in a nutshell the type of things that I've been doing. I have actually a brief kind of profile on the NYU website if you want to look me up. I've actually spent time in other universities before, including Columbia University, but I've been with NYU for about 25 years at this point, right? I've also taught like in the, what we call corporate training area. So I've I've also traveled quite a bit internationally, and I teach internationally as well. You will find that my teaching interests are very broad, simply because I build solutions. So I'm interested in pretty much anything that we can do in computer science to actually facilitate the creation of next generation solutions. So it goes through a lot of different topics that I have actually listed on this, including the cloud and machine learning, of course, and programming languages, software engineering, whatever, cybersecurity. And I'm kind of interested in where the new solutions are going in terms of Web3 and decentralized computing, things like the metaverse and possibly Industry 5.0 and Society 5.0. So that's a big interest of mine at this point in time. Kind of a brief summary as well of the stages that I went through. To summarize, I think I'm mostly interested today in transitioning research. And so I'm really you will see that I decided at some point to build platforms that I can use to do research and transition this research in the industry. So I will describe one of these platforms quickly now, and I will relate it to the topic later on as we speak, right? So what is this platform about? Well, before I get into this, obviously, we have different types of research in computer science that we do. Some of it can be exploratory, where we try to explain something that we see, like a lot of that is what we do in healthcare, for example. We also have like more experimental type of research. Actually, deep learning is an experimental type of research. We, cannot really explain why some of these algorithms work actually in detail, as we, sometimes they just don't work. So it's very experimental still today. And the types of research that I'm interested in are actually more the applied research and the finalized research, right, which I have kind of identified on this slide. So in the early stages of my career in the academia, I was doing a lot of fundamental pure research, and at some point I shifted to doing things that I could come up with solutions, practical solutions within 6 years, rather than looking for long-term 15 to 20 years type of return on research, right? So why am I interested in this type of transitioning research? Well, because, as I said, I'm interested in building things, and I like to make sure that I can apply my research to building customer solutions and discover what it is that customers need and create basically companies that can deliver the solutions, right? So that has led me to focus on one area which is very interesting to me and possibly to everyone today, which is advanced robotics in software and hardware as well. So what I refer to as intelligent autonomous network business solutions. So building solutions that can evolve basically, and that can evolve on their own without human intervention, and can reconfigure their components or machine learning models to actually be able to react to the environment in which they are placed. So I refer to those as evolutionary software solutions, and I will talk about a couple of them. I have developed like a platform that I have adapted to different industries. So you can see below on this second topic on this slide where I have like a platform called RoboFarm, and I have applied it to the financial industry, the healthcare industry, information management industry, manufacturing actually recently. And the way this platform works, it basically makes it possible for software to evolve. So what kind of software are we talking about? Well, we've been focusing on basically software robots that can do things like trade, replace humans, and try to actually make money on the stock market or any of these markets out there, or maybe build robots that can actually help people deal with conditions or diseases and whatnot in the healthcare industry. I also work with museums and libraries in trying to help them with their digital transformations, and I do that using robots as well. And obviously, we need robots in manufacturing, so the platform is also very useful there. So I'm going to give you a quick example of how this works for the financial industry. So this is a summary of how, let's say, trading works in the financial industry. So what we do is we kind of look at historical days worth of trading that we get from big banks like Citibank or Bank of America, and we actually mimic or actually simulate what it is that they do on a central exchange. And we built like a simulation of an exchange, and we can actually have bots operate on the exchange. And of course, we can figure out whether these bots are being effective by looking at whether they make money or lose money, and actually can achieve some trading goals based on what it is we ask them to do initially, right? So we basically replay some day worth of orders that came in the past. So you probably know that in the financial industry on trading systems, you can buy stocks. You can, let's say as an example, I'm talking about the stock market. You can buy stocks, you can sell stocks, or you can cancel your orders. So we can replay all these orders because the banks are supposed to keep track of days worth of data for like 10 years or so. So we have access to that. And we can build basically robots that can study the market and can make the same decisions, or maybe more intelligent decision, or they learn how to make decisions based on obviously training data. So they basically can combine these learnings to actually make more effective decisions that maybe some humans can make or brokers can make. And that's really the target of this type of system. So the system itself, or the platform, is pretty complex. You know, it's using an internal messaging system as the order book. And then you can see that we can plug some trading bots and possibly some generated agents that can mimic the market. And this platform enables us to study next generation trading. What I mean by that is, let's say, maybe in the future, instead of trading or getting like about 500 million orders a day, big banks will get maybe 2 billion orders. So we can already simulate this kind of volume, and we can actually create bots that can actually trade and be successful on this type of market. So this platform is actually being used at Citibank and Bank of America to actually teach institutional customers how to trade. And it's also used as an experimental platform to learn about trading patterns of the future. And just as to give you an example, you can see here, I have like a couple of trading bots, bot 1 and bot 2, and they can basically place orders on a trading queue and get an acknowledgement of the order and possibly a trade, right? And once they get a trade, there will be, obviously, they will augment their portfolio of assets with the assets that they purchased or sold, and then they will update as well. The wallet will be updated as well. So that's kind of a generic example of how these bots work. So we also have different types of bots. We have algorithmic trading bots. We have machine learning bots. We have reinforcement learning bots. This is an example of a reinforcement learning bot that can be trained based on trading data and can operate on the market as well. So what we do is we schedule competitions with these companies, internal competitions with folks like brokers that want to learn about how to trade better, or maybe institutional customers or students from universities, and we actually are able to create like robots that can achieve more goals, right, than traditional type of brokers. And we remember what these bots are, and we can actually use them in the future and provide them to the banks to actually do things like trading, or maybe detect fraud in the the trading platforms and whatnot. So there's a lot of things that we can do there. So this is an example of a competition that we ran, I think in 2000. This was during the pandemic, and I had students at NYU Shanghai that participated in this competition, as well as students from the US and Citibank folks. And basically we made it possible for them to use the platform, and we had about 30 people doing competition, and we had about 3 or 4 bots that were created as part of this competition. So this is just an example of what I do. I have a quick other example of how the platform can be used in the healthcare industry, where we've created kind of a watch based type of like iOS based, like basically an Apple Watch. We also have other types of watches that work like Android as well. And we place like a machine learning algorithm on the watch, and it makes it possible to detect conditions like high level of stress, for example. And then once you detect a high level of stress, you can actually ask the patient to play a game or watch a video or maybe listen to a song. We can connect the platform to an augmented virtual reality headset as well. So we can pacify the stress of people that have ADHD or possibly other types of stress syndromes, like children who have the ASD or Asperger type of conditions. And this has been very successful in the healthcare industry. I actually won Catalyst Prize last year, actually in the spring. Actually, I published that last year, but I won the prize this year, and we are actually using the money from the grant to actually harden the solution and actually make it available in the industry. So that's another solution that we have built. So of course I can provide my contact information if you would like to reach me and discuss these platforms. But without any more time being spent on this, I would like to delve into the topic of the day, which is the cloud platform as a service technology. So what is that all about? So I will try to quickly take a quick glance at the cloud, which you probably know about, like cloud computing, and look at what this platform as a service services are about, right, and how to use them. That's what I would like to do. So obviously we have a very large number of fields in computer science, right, before I get into the cloud. And combining the knowledge of all these fields, we have been able to actually, create something known as a cloud computing platform, and I will explain how this happened. Computer scientists are actually, we do a lot of research in computer science. What's nice about computer science and math is that we can actually invent things. Other fields like, biologists and other types of researchers cannot really invent anything. They can discover what exists. But in computer science, we have the luxury of being able to say, yes, we invented something. We can just make up stuff. Mathematicians can do the same thing, but I would claim that it's more difficult sometimes to use what it is that they create, but we make a lot of use of it in computer science as well, right? So you can see computer science may be at the center of this diagram. This is not meant to say that computer science drives everything else, but obviously computer science can be a way for people who do research in different industries or fields to actually make it quicker to find things, right? And that's really what the diagram actually shows here. And this actually results in a lot of different things being implemented in different fields. And until recently, or at least until about 2010 or so, it was pretty slow to actually do research because we didn't have ways to actually put solutions together very quickly to experiment or try to prove what it is that we were doing. This has been since then enabled by cloud computing platforms, which I will talk about now. So this is kind of an evolution that probably took us from the 1960s to 2012 or so, which I will kind of mention why this happened. But you can see that a lot went on to get people to use computers to start with and be able to connect them to networks and start being able to build solutions that are actually networked on this type of networks that I talked about. So what happened in 2012 is that a couple of technologies that we had been researching in computer science as well as applied in the industry started coming together. So there was what we call an inflection point between technologies like the cloud, mobile computing, analytics, and social media platforms that made it such that people in the industry started saying the connection between all these things, kind of saying, well, if we use these four technologies together, we can actually create platforms for people to use. And this was first the basic technology or platform that led to this advancement was cloud computing, which itself was, I think, at the center or as an integration of different types of technologies that we had worked on in computer science for quite a while, including distributed computing, internet technology, and whatnot, right? So that's a technology we converged to. And, you probably know how we use cloud computing today. Basically, instead of using one computer to do your work, like you see on the left side here, we can place what's called a virtual machine monitor on the machine and make it possible to create multiple virtual machines on the same computer. And these different virtual machines can have different operating systems, so it makes it easier to use computers single computers or big servers to actually share the resources across multiple, users, which is actually something that is done by big cloud vendors like Microsoft and IBM and Google and Amazon as well. And so one thing that has kind of shifted as well is what we used to call high-performance computing. So it's not always about how fast you can go and what kind of server you have access to, but it's also how fast can you feed data into the server. So we have more recently we came up with what's called heterogeneous computing machines that make it possible to use different types of processors, possibly multi-core, traditional chips or traditional CPUs, but also things like GPUs or neuromorphic type of computers or chips, or as well as maybe other types of technologies in the future, like quantum and whatnot, right? So the future computers will be probably machines that have different types of processing units integrated on the same, hardware. And some of these machines already exist, of course, and we use them. But the importance here is about throughput versus performance. So throughput is about how fast can you feed data to a processor so that the processor can compute, right? And we kind of face a lot of these challenges when we do machine learning, because in machine learning, we want to feed a lot of data into machines so that they can train machine learning models, right? So that's create machine learning models. So the cloud is really kind of a base platform that we use for most of everything today, because you can, instead of focusing on trying to get all the software and hardware on premise, like what's shown on the left, you can really focus on developing software by using machines and services that are provided by the big clouds or somebody else out there, and you can build your own application on data. So today I will focus on this vertical bucket that's called platform as a service, where you can build applications and store data on the cloud, and these applications leverage services that are provided by big clouds like I said before, like Microsoft, Azure, or Amazon and others, right? And so we have lots of different services. The traditional ones, of course, which are standardized, are the infrastructure services, the platform services, and the software services. But you probably know, I've heard about, or maybe I've heard about tons of different services that people provide and companies that provide those as well, right? So what's neat about the cloud is that it's usage-based and also elastic. So what you can do is you can say, I need, at the minimum, I need these resources. At a maximum, I need more resources. And the cloud is going to adjust to what you need as your applications run. So you don't have to go and buy a new machine because you are running out of memory or whatnot. The cloud, you can request from the cloud whatever you need, right? So to give you an example, and I'm kind of going to skip this slide here because I'm going to show you when the cloud platform works. You can place yourself as this little guy on top here. And what we typically do when we build platform as a service solutions is we leverage the cloud infrastructure, which is in green at the bottom here. And we build what's called cloud hosted, maybe hybrid solutions that some parts of them live on the standalone machines, and some parts of them also live on the cloud. So they're hosted on the cloud, at least part of them. And we make sure that they can use services that are provided by the cloud platforms, right? And these cloud platform services are shown as part number 3 on this slide here. So we use basically the green part, the bright orange, and then the light orange type of conduit to actually build applications, right? And you can also do other things as well, but I'm not really focusing on how to use these other ways of building cloud applications today. You can experiment with the cloud if you haven't done so very quickly by possibly going to some of the Jupyter notebooks that exist out there. And I don't have time today to show you some of this, but a lot of this can be done very quickly by running containers or images that are already available on the cloud, and learning very quickly by looking at some of the notebooks. I would recommend looking at Azure. Azure is actually providing a very good set of notebooks and has a lot of tutorials and whatnot. I'm not advertising for them, but I think they're very good in terms of educational resources. So you may want to take a look at what they do. So that's for the cloud, and this is kind of a snapshot of what the Azure cloud portal looks like. And you can see right there that you have access to many different services, right? You can have access to containers, you have access to management of containers, you have access to virtual machines, and there is an endless list of services that you can use on the cloud. In addition to virtual machines, we can also use what's called container technology. So you can see the difference on this diagram. If you have virtual machines, you can basically run different operating systems on the same server. With containers, you can actually run multiple applications or single applications within containers. And as long as you get a container management tool installed on your machine, you can actually deploy these applications without having to install them and reinstall them and whatnot. So it makes it very quick for researchers and developers of solutions to actually build things and actually experiment with new things. So this is really kind of the beauty of the cloud here. So why is it so important today to have this kind of platform? Well, simply because, as you can see on this very busy slide here, we have been able to build a lot on top of the cloud. So what we did is we took, and I'm looking at the top left of this diagram here, so we leveraged what we know about the internet, right? So the internet kind of, I showed you like around 2012, we had like mobile computing, social media, and the cloud technology, virtualization already available on the internet. So we were able to host the cloud platform on top of the internet, right? So, and then within these platforms, we can actually add services that focus on Internet of Things or machine learning or robotics, and you can see that it keeps going up in novelty, right? So innovation is what's being described in the y-axis of this diagram versus time, right, which is the x-axis here. So we've been moving from the ability to build more traditional type of cloud computing applications in the layer referred to as cloud to systems that we refer to as smart ecosystems that leverage things like machine learning, deep learning, natural language processing, and all of this to build new types of applications. And then we're moving into what we call the super society type of area where eventually we will be able to, to leverage autonomous robots to actually help us do things. In the smart ecosystems, we use technologies to help us understand what to do next, but mostly as assistant technology or assistive technology. In the top layer super society, we're going to basically leverage robots to replace what some of the tasks that humans do, so that humans can focus on things that robots cannot do, right? So that's kind of the idea. And so you can see on the right side that this approach or this evolution has led to, an evolution of the industry. And today we are still in this stage of Industry 4.0, where we're leveraging all these technologies to create solutions. And there is an explanation of what, the evolution has been since the early 70s when we had Enterprise 1.0 until approximately the internet came up in 1995, and you can see that since then, we've been going through stages of evolution of the enterprise, which is Industry 1.0 to Industry 4.0. So what is Industry 4.0? Well, you can look at it as giving you the ability to build intelligent digital technologies that can automate some of the solutions that we need in the industry and possibly provide insight to these people in the industry to operate their business more efficiently, right? So that's really what Industry 4.0 is about. And so this is a categorization that I've used myself to actually keep track of these new technologies, because if you see on this diagram at the top left here, we keep adding new things, right? Initially, we had IoT, big data. We now have machine learning and blockchain, and we keep going. So we need to have some sort of a way to catalog what's going on, and this is a good way to do so. So I created this kind of categorization, and using this categorization, I can actually build solutions that are more focused on each one of these categories, possibly using services that are provided by the other buckets, right? And so using this approach, we can start basically rethinking what exists, or maybe thinking what doesn't exist, possibly invent or reinvent, and then sometimes we just create new things, or we kind of rewire what already exists. So this is kind of the approach we can use today because we have these capabilities. So let's take a look now quickly as to what machine learning can provide on the cloud using the platform that I just described. So a long time ago, back I would say probably in the mid-90s or so, we referred to let's say high-performance computing as tasks that were in the bottom left corner of this diagram. So typically we use computers to do things fast, such as retrieve data from a database system, or maybe archive your data from your desktop to some sort of disk drive or something like that. But today we're more into the applications that are on the top right of this diagram, which is how can we reason about things, right? So if I am in an insurance company, how can I tell quickly whether somebody can, what kind of, if it's insurance, what kind of insurance product can I sell to this person at what price, right? Or so this is more like actuarial analysis, or maybe risk modeling would be credit card type of things. Can I give a credit card to this person, and can I make a decision within, let's say, a minute or so that I can give the card to the person right there on the web, right? So these solutions need obviously things like we refer to as machine learning to kind of make these decisions very quickly. And we've been working. Obviously, machine learning has evolved since the I think I started studying back in the 80s in the US, and so back then we had actually artificial intelligence, but it was not the type of machine learning technology that we use today. I guess we had the algorithms, we had everything we have today. We had neural networks back then. We could not actually use them because we didn't have the fast machines that we have today to train them. We didn't have the data, and the algorithms were not as efficient as what they are today. So we have been spending the past good part of the past 20 years improving the algorithms, and now we have a good set of predictive algorithms that we can use to experiment with, and I will focus today on the predictive experimental bucket of side of this diagram that I'm showing here, right? So what are we doing in these types of solutions that use machine learning and to create like smart ecosystems? Well, a smart ecosystem is basically a system that can give you immediate insight as to what you need to do, right? So prior to being able to do that, we were only able to, let's say, look at the past, which is looking behind, which is hindsight. And we were basically trying to look at reports of how well did we do with the business over the past year, and maybe we could figure out, what were the problems and try to avoid them in the future. Or we could do statistical type of predictions, and that's looking forward, which is called foresight on this diagram, right? But we could not do insight. We could not tell people, this is what you need to do right now to improve your business. Luckily, starting probably back in 2012 or so, because of the cloud and all these technologies that came together, big companies were able to start doing this. And you have like retail stores like Walmart in America, for example. They have like RFID tags on everything that's on the shelf, and they can track pretty much what they're selling in real time. And if they don't sell some products, they can actually ship what doesn't sell to other stores in America very quickly using their trucks. And so they can optimize their sales by using, analytics on the fly pretty much, because they have access to this kind of insightful technology, right? So there's been a lot of evolution. Like I said, if you look at this diagram between the early days of analytics to what we can do today with predictive analytics and prescriptive analytics based on the example of Walmart that I just gave you now, right? So one thing kind of is different about what we do in machine learning versus what we do in traditional programming. In traditional programming, I may ask you to, let's say, build a little calculator program that can add two numbers or multiply two numbers. You're going to be able to do that because you know math, you know how to add numbers, and you know what the algorithm is about. So you know how to, if I add 2 and 2, I'm going to get 4, and I can generalize this and build a little program in the programming language of my choice to actually do this. In machine learning, it doesn't work like this because we do not know what it is that the program is supposed to do. We don't have the algorithm itself, right? So, for example, if I ask you to tell me whether I'm giving you somebody's symptoms, they're sick, they go to the doctor, and I'm telling you these are what the symptoms are. Can you tell me whether this person has a given disease? Well, you will not be able to do that. Only doctors can do that, not based on programs, but based on their knowledge of having been doctors for a long time. So what we're trying to do really in machine learning is trying to approximate this quote-unquote function that the doctor is using to make this prediction, right? So, and we do that by using a lot of data that we have actually collected from, let's say, hospitals in that case or whatnot, about people who have the condition. and we take a look at the symptoms, and we can predict, based on new symptoms, whether that person has a disease or not, right? So that's kind of a difference in computing between the two models of traditional programming and machine learning. And more recently, I would say in the past, 10 to 15 years or so, we kind of shifted the way we used to do data mining to doing what's called machine learning. The difference is that we're not expecting people to apply algorithms to data. We are kind of expecting to be able to build programs that can automate the whole thing. And this is what machine learning is about, right? And, I'm going to skip some of this here. So this has obviously led to an explosion of data science type of research. And you probably know that you can get data science degrees, like master's degrees now, rather than computer science degrees. But you have to be careful about that because you still need to know a lot of computer science to do data science. So don't lose track of that, right? So although you can get different degrees, it's also good to know about some of the topics of traditional computer science, because at the end of the day, if you're going to do machine learning, you probably need to know a lot about computer science to start with. So this evolution has been going on for quite a while. You can see like 70s up to where we are today. And we are now not just with big data. Big data is something that I refer to as shallow machine learning. We are now going to, we're in the era of deep learning, right? Which is something where we can look at problems that have a lot of labels to them, right? So when I look at a disease, for example, like if I look at a condition, for example, like diabetes, there is only, I would say, two labels. You look at obesity and possibly like, blood oxygen or some other type of factor. So that's two labels. If you're looking at an image and you're trying to recognize whether there is a dog or a cat in the image, you have maybe 3,000 by 3,000 pixels. You got 9 million labels. So we need a better type of machine learning to actually do this type of things. So there is a whole workflow or data flow actually to be aware of when you do machine learning, which is it's not just about building models that can predict things. It's also about making sure that you store the data properly and that you make it available to people who build these models. So there is a lot more to doing machine learning than just using algorithms and building models, right? And so we also have to be aware of the fact that there is a lot of data that's coming in from different sources, and luckily we have the cloud to store all this data today. And some of the data is dynamic. It's coming from social media sources. So you can think about human beings as being a form of sensors that are providing a lot of data to researchers out there. So that's kind of a very interesting way of looking at what people provide through the social media channels, right? So I'm going to skip a couple of these slides here. Most organizations today have to think about being connected and being able to move quickly in terms of the solutions that they're building for people. And these solutions also need to be adaptive or evolutionary to adapt to the context in which they are used. And I gave you an example at the beginning of an evolutionary application, like which was a trading system application where the market keeps changing. So it's not predictable the way it will change. So if you want to actually be successful on the stock market, you probably want to evolve very quickly and change the way you trade, right? And we can teach robots how to do that. And if we can fingerprint the market, we may be able to get these robots to be successful again and again, but that's difficult, right? So a lot of what we do today with machine learning is we have services that are shown on the right side here that we can apply in machine learning and that run on the cloud and that can do analytics for us. And what we can do with this is we can build applications that can do big data analytics, which is shallow machine learning, or can go all the way to doing cognitive computing. So the difference there is, are we trying to mimic some of what humans can do? Something like, for example, human can see, can hear, can smell, can touch. Can we emulate or simulate all this using machine learning by teaching basically a machine learning bot to based on data that you have to learn how to basically see and recognize things, for example, versus doing simpler things, which may be able to, for example, detect a disease and possibly predict a disease, right? So there are different approaches that we can use, and you want to be careful as to what you do with machine learning because it could go from very simple to very complex, right? And so luckily we have categorized different approaches to actually use the technology today. So there are lots of simple APIs that exist. For example, Google has vision and speech APIs that you can use, and other companies have them too. So you can recognize what people say, and you can translate what people say in different languages, or maybe you can recognize when an object is. So typically there is not much to do there. You can pass your image or your text to a cloud service, and that will actually do the trick for you, right? So you would just need to write a little program. You don't have to build the model. When you don't have this type of support, then you can run what's called a pre-trained model that may be available out there. And there's models like, for example, the COCO dataset and the associated machine learning algorithms that can actually recognize images for you. And, companies, again, like the big cloud provide these types of models out there, right? And so that's a second way to do things. The third way to do things is there is no pre-trained model that you can use. Then you can use an existing design of machine learning architecture and train it using your own data set. This is more involved. Obviously, you have to have your own data set to do this, but you don't need to come up with the neural network design that's going to help you do things. And the more difficult solution at the bottom is the one where there is no architecture that exists of machine learning models, and you don't have a data set, so you have to do everything from scratch, right? So the second, I'm going to give you examples of these four approaches. So this is how to use an API. So you can see here I'm using an API. I'm just basically passing an image to the API, and it's coming back with a score as to what does this person's face say, right? What is the prediction about whether this person is actually happy, unhappy, what not. And you can see that you can do that pretty simply by sending an image to that API, and you can get an answer back, right? Using a pre-trained model requires a little bit more work. So in this case, you can use, let's say, a convolutional neural network that already exists. They may have the data already, and ResNet 50, for example, has been trained with data, so you can actually use it to recognize some images and whatnot. A lot of these, a lot of the data that was used to actually train these algorithms came from a project called ImageNet, which was actually still running for about 15 years, where basically we crowdsourced the description of images on the internet, and based on that training data, we can train vision recognition algorithm like ResNet, right? So third type of way of doing things is building your own, bringing in your own an existing model. So you can use a collab model, and you can train it with your own data, and then be able to actually do things that you want. And the more difficult way of doing things is to use frameworks like TensorFlow or other frameworks like to actually, like PyTorch, for example, to actually do everything from scratch. So here you have to bring your own data, you have to program your own algorithms and whatnot. So that's more involved. So this is a very quick description of an example here. Let's say I have some patient data that's anonymized. You can see here patient ID has been anonymized, right? Also, you have like 4 labels that describe the condition, which is actually hyperlipidemia, which is some sort of grease in your blood. And then you can see that we know that some people have the condition or not. So in the last column, you can see 1 if the person has the condition, 0 if the person doesn't have it. So this is the type of data that you need to train, let's say, machine learning model. So you will need to have an algorithm that you are using. So you need to train this, use this algorithm and create a model by training it, right? And in this case, I'm using a logistics regression function with z equal beta 0 plus beta I multiplied by xi. I is 1 to 4. And if you do that kind of training, you will figure out that you can actually predict whether new people have the condition or not, which would be in the diagram at the bottom right would be people who actually don't have are not in the patient ID list could actually still be predicted as having or not having the condition by running their symptoms into the formula. And that's kind of the way we do it here. Now, there is really no good way to select which algorithm you should use. It's really very difficult to actually build things from scratch, or you have to do a lot of experimentation. This is why approach number 4 takes a lot of time. So this is just an attempt to actually try to see which algorithm is the best to use. And you can see that it's difficult to do. At the end of the day, what you will find is that some of these algorithms are best in certain cases, and you have to kind of do a lot of trial and error type of work to actually build the whole thing, right? Luckily, we can, we have a lot of case studies and knowledge that we have already acquired, so we can cut to the chase and go and do things faster. Deep learning, takes a problem to a more an even more difficult, situation, because instead of having just, let's say, 4 labels like I do here, you can have very large number of labels, like, for example, as many pixels as you have in this image here. So to do this, we apply things like, neural networks as the algorithm, and we train the algorithm by figuring out how many layers do you need first. This would be the architecture of a neural network. So you will probably need to decide how many internal nodes you need, how many layers you need internally, and how many input nodes you need, how many output nodes you need. So in this little thing here, you could see on the left side, I could say I've got 3,000 pixels altogether, or maybe 9 million. And so I would have as many inputs as I have pixels there. I would have as many layers as I need to remember all the patterns that are in the image, and possibly as many nodes per layer. And then the output could be, I want to know if there is a cat or a dog or both in the picture. So I'm going to spare you the details, but trying to not only come up with the right design for the algorithm, but also programming it and figuring out how to feed the input and coming up with the right weights and also values in the nodes is a very time-consuming type of exercise that would take a lot of steps, right? So the good thing is that we came up with an algorithm called the gradient descent algorithm that makes this process much faster, and we can actually kind of train models using machines without human intervention, and we're able to do that kind of reliably since about, I would say, 2010 or 12 or so. And we have been using a lot of that in the industry. It's not by no means perfect, but it actually does the job for a lot of things, right? And we don't know if it is the right approach. I would not make a determination at this time as to whether it mimics anything that humans do, like some people do, but I think it kind of approximates what people do in some cases. So I'm going to spare you some of the formulas here, but what we basically are able to do is mimic vision, for example, and it typically takes a human from anywhere from 20 to 160 milliseconds to be able to determine what an object is once you see it. So if you see a ball or a stone, you have to first decide whether it's a ball or a stone, right? So it would take about as much as 100 milliseconds to decide that, to actually figure out that. And then after that, you have to make a decision as to what to do. So which is like you can run to avoid the stone, or you can catch the ball. And once you know that, you can tell your nervous system to move your legs or arms to do something. So it takes altogether about 200 milliseconds. So we can go much faster with computers, but we haven't figured out yet how to do the decision part of it. So we can recognize things, we can do perception of like vision, hearing, and other things, but decision making is something that we haven't quite figured out yet, right? And I've kind of been working on a solution myself, which I used in the platform that I described earlier, but I don't have time to get into much detail of this. So what's interesting about AI altogether, which is based on, basically think about AI as a set of processes that, we're trying to basically mimic human processes rather than generic processes. We've kind of stepped back a little bit. Initially, we kind of used a lot of data to try to mimic what these processes do. We have kind of figured out now that we need to be able to explain what it is that the algorithms do, because if you can't, that you can't use these algorithms in the industry or for real life applications. And so we're kind of in that phase of explainable AI today, right? So now it's not just about using a machine learning algorithm, but about why does it work or why is it that it doesn't work. Sometimes you build things that are supposed to work, they don't, right? So there's tons of real-life applications that you can build based on this technology. Initially, we apply the technology to be able to recognize handwritten digits. Actually, a fellow friend of mine, Yan LeCun at New York University, actually came up with this back in the 90s, like mid-90s or so, as part of his PhD. And we can do that fairly fast. We can apply the same method using different algorithms to recognize acoustic inputs and predict what it is that maybe the weather would be altogether using a program like this, right? We can also recognize very, I would say, complex type of biological forms. In this case, you can see that we can do that with what you see at the bottom is called a confusion matrix. So we can do that, pretty accurately, right? So sometimes the algorithm gets confused and it thinks it's one versus the other. But in general, I think it does pretty well. We can apply this technology in the healthcare industry, and we can basically pass in the input from sensors through the network to the machine learning algorithm so they can actually produce predictions for people to use. We can equip people with sensors today and release them from the hospitals, right? And we can monitor them in real time and predict their condition in real time. And also, you can equip them with a little robot on their phone or whatnot that will tell them what to do if they have something like a heart attack or something, in real time, so they don't actually are victims of that. So there's a lot we can do with technology, especially with the fact that networks like, we have like 5G today and other types of wireless type of network technology that makes this whole thing very, very possible today. And of course, we have applied all of this to technologies like autonomous cars, and there's a lot of different technologies using machine learning today. So the question is, how much of this is actually usable and reliable today in the industry? So, self-driving cars, well, we're still in the process of kind of testing things and deciding whether they should be used as a mainstream solution. Drones, same type of things, right? We can actually do delivery by drones. That's something that's possible. Reliability is yet another things we need to study. A couple of different examples of this here, which I really don't have time to go through here. There's also an evolution of robotics that has actually kind of evolved into using this technology as well. And you can see that, it's been going on for quite a while. We have robots that do look good today. I think, there's a difference between what we call robotics and software robotics. People in the robotics field do not consider software robots as actual robots because there is no hardware associated to them, but we're trying to actually work together. This is an example. Actually, I will show you this one quickly here. You can see how much we can do with hardware robots. This is actually a company called Boston Dynamics. You may want to look at their website. It's pretty amazing that these machines actually can do what they do. Of course, that technology can be applied to do remote surgery at some point and whatnot. So tons of different applications in different fields, right, altogether. I have done a lot of different projects myself, probably in the thousands actually, with students at New York University, because I do that on a recurring basis every semester for quite a while. And we have been looking at applying this technology in different contexts. I think in this particular application here, you can use this is actually something I was doing in China in 2019, where we were able to look at the table and pretty much predict what's around the bottle, including the bottle. And the algorithm, this is just using an API, the Google API actually, and it's able to actually tell you, pretty accurately that this is a bottle of water, that there is a person sitting there, not sure if it's a man or a woman, but there is a laptop, a table. So we can do some interesting stuff that can be very functional. I'm kind of applying this today to do something called teleportation. Or, Microsoft has been working on something called holoportation. So it's kind of similar, but making it possible for people in different locations to collaborate through basically virtual reality environments. So you could be in a classroom in different locations and have the illusion that you're actually in the same classroom with them. So I'm going to keep starting. respects here. So things are evolving. Obviously, there's a lot going on, and we're moving towards what's called the metaverse, not the social media metaverse of Meta, but maybe more kind of what the next generation of internet, Web 2.0 is about. So Web 3.0 is kind of blockchain plus Web 2.0. So maybe Web 4.0, 5.0 is what companies will call metaverse in the future. I think in the US alone, we probably have around 600 companies that already have like metaverse type of enabled equivalent of websites through which they can sell their products. So to kind of, I think there's a lot to talk about. I just want to finish this here. So obviously, machine learning can be used through the cloud and combined with other technologies to build interesting solutions. We are moving towards even more advanced capabilities, such as neuromorphic computers that basically mimic neurons. And you can see here one of the Intel solution that's a low heat I would say they have like 4 boards included in this. You have 32 million neurons on this particular setup here, and you can use this to do computations in neuron fashion very fast. We obviously also have quantum technology that we are using for a similar purpose to accelerate some computations as well. We also are making a lot of progress in nanotechnology, being able to reduce the size of things to a level that's unbelievable, actually. We are able to do a lot of progress in networking. We're moving to 6 and 7G now by improving we switched over the frequencies that we use for networking, and we're able to go like about 100 times faster than we were before. We also changed the antenna design now, so we can have like millions of connections per antenna instead of 4,000. So that facilitates a lot of this. And obviously, we're moving towards Industry 5.0, which is kind of an interesting move that basically makes it possible for us to not just focus on technology, but focus on the well-being of people and possibly the well-being of humanity and the planet altogether by using and applying this technology. Right? So that's kind of more of the focus of the future. And you can see an evolution of to Society 5.0, where the whole idea would be to have a super smart society by making all these technologies available to people. Right? And the same is true of education, believe it or not. We're also moving towards education 5.0, which is kind of a variant of education 4.0 that makes it more student-centric, right? And based on all these technologies that we have. So I will stop here and we'll take any questions you may have. I'm sorry, I wanted to have like 5 minutes, but I only have a couple of minutes now. So hopefully I can answer questions that you guys have. So thank you for listening, and I hope this was informative. And let me know if you have questions. I would be glad to answer them.
Thank you very much, Professor, for your sharing today. So if you have any questions, please feel free to communicate with our professor directly. 同学们，如果有任何问题的话，欢迎大家直接跟教授交流，或者把你的问题给我们方面。我们应该是在让教授提问。那还有问题吗？ Professor, can you see the chat? There is a question from my student.
Okay. Well, so I think it's been a pleasure to to share this information with you today. And again, if you would like to connect or whatnot, feel free to do so. And thank you for giving me a chance to talk about this topic today. Okay, thanks everyone. You take care now. Bye.
Thank you. Bye bye.
Thank you. Thank you. Bye bye. Thank you.